I'm Adam. This is the Machine Tech video blog, and today I'd like to talk to you a little bit about the different types of centrifugal pumps. When it comes to pumps, most operators only care about inputs and outputs. How much pressure does the pump generate? How much flow does it deliver? How much power is required to run it? But maintenance people need to know a few more details about the inner workings of these machines if we're going to be on the hook to keep them in good running order. We don't have time to cover the specifics of centrifugal pump operational theory here, but it was the topic of a previous video. Just as a refresher, centrifugal pumps get their name from the way they impart energy to fluid. When fluid enters the pump, it comes into contact with the rotating impeller and is thrown outward by centrifugal force. It travels through a specially shaped chamber called a volute and exits the pump at the discharge outlet. All centrifugal pumps share this basic operating principle, but there are a few possible variations among them. There are 5 primary design elements to consider: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. There are a few special designs as well, but those will have to wait for their own videos. There are 3 types of impeller: open, semi-closed, and closed. The simplest impeller construction is the open impeller, which consists of nothing more than a few curved blade-like vanes equally spaced around a hub on the rotating pump shaft. Large, unrestricted fluid pathways allow this type of impeller to pump fluid containing mud, leaves, twigs, sand, sludge, spray paint caps, dead birds, you name it. And that makes them ideal for trash pumps or this pump, which actually came out of a wastewater treatment plant where it was pumping raw sewage. It was necessary to handle gritty slurries with soft solids. And it even has special chopper blades just ahead of the impeller to help break down very large solids. Ooh. If the vanes are mounted on a backing plate called a shroud, then the impeller is a semi-closed impeller. And if the vanes are sandwiched between 2 shrouds, then it's a closed impeller. Closed impellers are more efficient than either semi-closed or open impellers because the fluid is directed through very well-defined pathways. That means that more of the fluid is pumped out into the system and less of it is just recirculated around and around and around inside of the pump. Of course, the trade-off is that they can very easily get clogged with debris. Whichever style of impeller is used in a pump, it's mounted on a rotating shaft and needs to be supported by bearings inside of the casing in one of 2 ways, either overhung or between bearings. In an overhung configuration, the impeller is cantilevered on one end of the shaft and the bearings are offset to the other side. This configuration places the suction and discharge piping at 90 degrees to one another, with the inlet directly in front of the suction eye at the center of the impeller. This is why pumps with overhung impellers are more commonly referred to as end suction pumps. End suction pumps are abundant in industry because they're relatively cheap and easy to manufacture, but they do have one big disadvantage arising from the way that fluid travels through the pump. During operation, there's a zone of low pressure at the suction eye where fluid first enters the impeller, and a zone of high pressure at the outside rim of the impeller where the energized fluid is released into the volute chamber. This high-pressure fluid also has a leak path to the backside of semi-closed and closed impellers, which totally throws off the balance of pressure. The net effect is a constant axial force, or thrust load, pushing the impeller toward the suction inlet of the pump. You can compensate for this effect a little bit by installing beefier bearings capable of handling thrust loads, or drilling holes through the impeller shroud to allow for some pressure equalization. But neither of these are true fixes for the problem. A more effective solution is presented if the impeller is supported by bearings on both sides, called a between bearings configuration. Not only does supporting the impeller with bearings on both sides generally improve shaft support, it also means that many of these pumps can employ symmetrical closed impellers with double suction. Since there are identical low and high pressure zones on both sides of the impeller, this effectively eliminates thrust forces due to pressure imbalance. And this design has another key advantage. The suction and discharge piping are normally positioned parallel to one another on opposite sides of the pump, and the casing is split axially so that just by removing some bolts and pulling the cover off, maintenance technicians can access the rotating assembly inside the pump without removing the whole pump from the system. This axially split design is why pumps with impellers between bearings are more commonly referred to as split case pumps. Now, those are all pretty convincing reasons to go run out and get yourself a split case pump right now, but of course there has to be a disadvantage. Because the manufacturing processes and the sealing requirements for split case pumps are much more elaborate than for end suction pumps, they're also naturally more expensive. Next on the list of design elements is orientation, either horizontal or vertical relative to the pump shaft. Centrifugal pumps are usually oriented horizontally, but they can also be oriented vertically. Vertical pumps are used in plants where a reduced footprint and space savings are desirable. And you may also find one down at the bottom of a well or sump connected through a long line shaft to the driver above. This brings us to the mounting method of the driver, usually an electric motor. There are two options for transmitting rotational force from the driver to the pump. Either frame-mounted or close-coupled. If the pump and driver are two separate units, as they are here, then the pump and driver shafts will need to be connected by some type of a coupling. Now, couplings come in all shapes, sizes, and styles, but one characteristic common to all of them is that they require proper alignment of the shafts, and that can be a very finicky process indeed. To help facilitate and maintain machine alignment, the pump and driver are mounted on a common base plate, or in the case of units oriented vertically, the driver is mounted above the pump on a structural support called a C-frame. This type of pump and driver unit is said to be frame-mounted. For large, heavy equipment and for all split-case pumps, frame mounting is really the only way to go. A second option is the close-coupled mounting method, in which the pump and its driver share a common shaft, with the impeller mounted overhung on one side of the driver shaft. In this case, there is no need for a coupling or any of the extra labor required to perform sensitive alignment procedures. However, since both the pump components and the driver components are supported on the same shaft just by the bearings in the driver, this mounting method is really only appropriate for small and medium-sized end suction pumps. Finally, a pump can be classified by how many stages it has. Most pumps have one stage with a single impeller and a single volute chamber. However, some pumps have additional stages connected in series to help boost the pump's discharge pressure. The idea is that the first impeller adds energy to the fluid and then feeds it into the next impeller, which adds more energy to the fluid, then feeds it to the next impeller, and so on and so forth until the fluid is eventually discharged into the system. Well, there's your introduction to the different classifications used for centrifugal pumps: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. And that's it for today from the Machine Tech video blog. I hope you learned something.